I am going to walk you through the post-lab analysis for Lab 7, the organic unknown. This is actually a pretty tricky post-lab. In my opinion, it's the hardest one that you're going to do all quarter long. And it's a hard one to do a tutorial on because everybody's data is really, really different in this experiment. So the first four questions on this post-lab assignment is just you reporting data for your unknown. When you get your unknown into the round bottom flask, the chalkboard in the lab is going to display some data for your unknown. It's going to end up shows up like right around here, kind of in the middle on the right hand side, and you're just going to copy that data down from your chalkboard. You're going to write down the unknown number, so you're going to have some sort of identification number. The compound is going to tell you, or the lab is going to tell you, the boiling point or the melting point of your unknown. The boiling point is going to be abbreviated BP, melting point is going to be abbreviated MP, and this is not specified, but it's being measured in units of degrees Celsius. So you're going to get a number down here, let's say maybe it's 150. You're going to need to convert that into units of Kelvin. The lab software is not going to do that conversion for you, but you will need it in units of Kelvin eventually. So you'll write that down, do that conversion from Celsius to Kelvin. You'll also be copying percent composition data for your unknown. So it's going to tell you, let's just say maybe it's 75% carbon, 25% hydrogen. Again, this is going to be displayed on the chalkboard. And this is all the information that's going to show up on the chalkboard. Now, some of you are going to be lucky, and your percent carbon and your percent hydrogen are going to add up to 100%. And that just makes this post lab a little bit easier. Not much easier, but it makes it a little bit easier. Some of you are going to be unlucky. Some of you are going to have your percent carbon and your percent hydrogen not add up to 100%. And the software is not going to tell you what else there is in the compound. So if you have a case like this, it would say 75% carbon, 5% hydrogen, that adds up to 80%, and it doesn't tell you anything about what's going on with the other 20%. All that you can say for now is that you have 20% some other atom, you don't know what it is, and you're coming up with this number yourself because this 20% is not going to be on the chalkboard. So this is, and don't panic if you're in this situation because it's not that much extra work. So the next thing that you need to do is figure out the molecular weight of your unknown as determined by the mass analysis. And this is something that a lot of students get wrong. So definitely want to pay attention to what's going on here. So this is the diagram that you want to focus on. This is an example of some mass analysis data. Yours, chances are not good that yours would look exactly like this, but it might. There's a lot of variation in the way this data shows up in this is called a mass spectrum. So don't expect to have a similar looking graph. You may have just one single blue peak on the right-hand side and literally nothing else. You may have a large peak on the left-hand side and a bunch of small things. You may have way more data on here or way less data. Like I said, there's infinite possibilities of what you might expect to see when you're looking at your mass spec. They're all going to look different. The bottom axis here is the mass in units of grams per mole. So your scale, my scale goes from 0 to 70, or actually probably goes to 80. Yours may be a smaller scale or a larger scale, just depends on your data. And then over here on the side, this is representing relative abundance of different chunks of the molecule, and you don't need to pay any attention to what's going on over here at all. This doesn't have any bearing on what we're doing with this data, so you can ignore that completely. Now, one of these blue bars in this graph is representing the molecular weight for the molecule, and your job is to find the blue bar that actually represents molecular weight. Most people, for logical reasons, their eyeballs gravitate towards the largest blue bar and they say, boom, that's it, that's my molecular weight. Read down on the axis. This particular large blue bar here is showing up at 61, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is showing up at 66. So this would mean that my molecule's weight was 66 grams per mole. And that occasionally is correct. In this particular case, it is correct. This blue bar here is the molecular weight. 66 grams per mole is the molecular weight of my unknown. But that is not always how it works out. You're not always going to be looking for the largest blue bar on your graph. So what I'm going to do is just I'm going to use my pens here to kind of change this graph a little bit. So I'm going to change these blue bars over here. Just going to make them all a little bit bigger. Like that. And then I'm also going to change the blue bars that are on the right-hand side. So this gray doesn't match up perfectly, but let's pretend like that gray matches up perfectly. And I'm just kind of erasing. I'm making these little bars smaller. So let's say that this is what your graph looked like. And for a lot of students, if this was their graph, and your goal again is find the molecular weight, a lot of people's eyeballs are going to say, boom, there's my largest blue bar. That right there, that's my molecular weight. That looks like it's at about 39 grams per mole. And that would be wrong. This would be an instance where the largest blue bar is not your molecular weight. When you're finding your molecular weight, what you want to do first of all is recognize there's a pattern. No matter what your graph looks like, there are going to be all these little clusters of peaks. So notice that the peaks come in clusters like this. So my graph has 5 clusters of peaks. So find all of your little clusters, and then what you want to do is ignore all of them except for the cluster that is all the way on the right-hand side. So we're just going to pretend like these ones do not even exist. We just want to focus completely on the cluster of peaks that is furthest to the right in this graph. And when we're looking at this cluster of peaks and ignoring everything else, we want to find the largest blue bar in this cluster. That is going to be our molecular weight. So it's not necessarily the largest peak, it's the largest peak that is furthest to the right and also highest in abundance. It's not the peak that's furthest to the right, and it's not the peak that's highest in abundance. It's the peak that is furthest to the right and highest in abundance among the things that are furthest to the right. Like I said, this is the trickiest part of the whole entire post lab. This is where a lot of students get confused. So let's take that 66 grams per mole. This data is so like, I'm just writing and making up. I just made up all of these numbers. They're completely inaccurate, but we're just going to go with it. So once you get your molecular weight, you're going to calculate the number of carbon atoms in your molecule, and you don't have to calculate the number of individual atoms. You can just calculate the number of moles of carbon atoms in your molecule. You're going to do that by taking the molecular weight of your molecule. So your molecule is 66 grams per mole, and you're going to multiply that by the percentage of the molecule that is carbon. My molecule is 75% carbon, and this is going to tell you the mass of the carbon atoms in the molecule. So assuming that this was my data, 66 times 0.75 is 49.5. That means that I have 49.5 grams of carbon in my molecule. And then I'm going to do a gram to mole conversion for carbon. 1 mole of carbon is 12 grams of carbon, and this is going to be 4.1 moles of carbon, which I'm going to round to a whole number, 4 moles of carbon. And your data will probably be better than this because this is completely made up data. I'm surprised that it came as close to 4 as it did. Then you're going to do the exact same thing for hydrogen. So we've got a molecule that is 66 grams per mole, and my data is telling me that 5% of that mass is hydrogen. So I'm going to multiply by 0.05, and that tells me that 3.3 grams of my molecule are coming from hydrogen atoms. And I'm going to convert that into moles of hydrogen. 1 mole of hydrogen is approximately 1 gram of hydrogen, which means that I have 3.3 grams or 3.3 moles of hydrogen. This is not great data, but I'm just going to round it down to 3. And then if you are lucky, so if you were one of the lucky people that didn't have that your carbon and hydrogen added up to 100, you don't need to do problem number 8. But if you're one of the unlucky people that your carbon and hydrogen didn't add up to 100 and you do have something else in your molecule, you do have to do one more step here, which is basically the same thing. You're going to determine the mass of the other atom in your molecule. So you're going to take your molecular weight one more time, 66 grams per mole. You're going to multiply by the percentage of the molecule that is another atom. 0.2% is what I got. 66 times 0.2 is 13.2 grams of whatever this other atom might be. Now, we cannot convert these 13.2 grams into moles because we don't know what the other atom is. We don't know what its atomic mass is. So this is kind of, as far as we can get with this calculation. There's 13.2 grams of some other molecule or some other atom. So then what you're going to do, question number 9, and again, question number 9 is not something that you have to do if your carbon and hydrogen adds up to 100. 13.2 grams of another atom, we'll say other atom, you have to make a reasonable prediction about what that other atom might be. You're going to want to have a periodic table handy for this, and I'll tell you that 13.2 grams, if that's what you got, that would be horrible, because that's not going to work out at all for us, but we're going to play the game. So first of all, in the instructions, I'm telling you that whatever this other atom is, it's most likely that you only have one of them. So it's most likely that there's only one. There is a slight possibility that you might have 2 of these other atoms, but most likely there's only one. So what we want to do is go to the periodic table and find the atom that has a molecular weight or an atomic weight of 13.2. So when we go over to the periodic table, we've got boron, which is 11, and carbon, which is 12, and nitrogen, which is 14, and there's no atom that has a mass of 13 or anything like 13. So this is happening because I just arbitrarily made up data that doesn't make any sense. You're going to get something that is way better here. Like maybe you're going to get 16.2 and then you'd say, oh, that must be an oxygen. Or maybe you'll get 14.2 and you'll say, oh, then it must be a nitrogen. You're going to get something that makes sense. That's not a 13. There is a possibility that you might get something like 28 grams. You might have something that says 28 grams. And if it's 28 grams, there's silicon, which has 28, but there's also nitrogen, which is 14. And nitrogen is a much more common atom than silicon. So if you had 28 grams, it's more likely that you have 2 nitrogens, and it's not very likely that you have 1 silicon. And that type of stuff is described in part 1, step 1. That gives you some suggestions about what these other atoms might be. As far as my case goes, I don't know what to say here. If I had 13.2 grams, if I was doing this experiment myself and I got 13.2 grams, all that would tell me is that I did something wrong somewhere, and I would go through and redo my calculations or double check my molecular weight and make sure that I was actually looking at the right bar, because something is definitely haywire. And for this, just for the purposes of this, I'm just going to say, oh, oops, let's say that we rechecked our calculations and found out that it was actually 14.2 grams. And in which case I would say, oh, okay, that must mean I have a nitrogen. So the next thing that we want to do is propose the molecular formula of the unknown. So now this is like, no matter who you are, no matter what your data is like, we're all doing this step. Propose a molecular formula. That's going to come from the moles of carbon, the moles of hydrogen, and anything else that you might have present. I had 4 moles of carbon, 3 moles of hydrogen, 4 moles of carbon, 3 moles of hydrogen, and 1 nitrogen. So there's my molecular formula. And then I'm going to find the name. How am I going to find the name of this molecule? Well, we have to first figure out what the molecule is. So in your instructions, it's going to tell you to go to the NIST website. The URL for that is in your lab instructions, and you are going to search by molecular formula in the NIST database. And in that set of data, you're going to see a whole bunch of molecules that have the same formula as yours. There's going to be many, many, many different molecules that have C4H3N. Actually, not that. But your molecular formula, you'll have tons of different options, and you'll just start clicking on all of them and looking at all of them, looking at their mass specs. And this is an example of showing there's a mass spec that came from the lab software, and here's a mass spec that came from NIST, and we can see by looking at them the similarities between these two peaks, the two spectra. They have really similar shapes. They're not completely identical, but they are really close to identical. They're almost exactly the same. And so with this, when I see this NIST spectrum and compare it to this Beyond Lab spectrum, I can say these two spectrum are the same. They are coming from the same molecule. The NIST website is going to give me the name of this molecule. So on the NIST website, the name is going to be written down, and then that is what you will copy into problem number 11 on the PostLab. You're also going to include in your analysis, in your submission, a picture of the mass spec from your lab and a picture of the mass spec from the NIST website. So you can show me something like this that shows the two spectra side by side so that I can see that you correctly found your unknown somewhere on NIST.